Find dy dx given that y over x plus 1 over y plus 1 over x equals 1. Okay. So for this one, normally we're given like f of x, which is basically y, equals something. And we're told to find f prime of x. Well, this time they ask for dy dx, which is similar to f prime of x, but since x and y are all on the same side, it's easier just to ask for dy dx. So one of the things we could do is we could rearrange things so that we have like 1 over y equals 1 minus 1 over x, and then we take the reciprocal, flip everything over, and we'd have y equals 1 over 1 minus 1 over x. Maybe we could do it a little bit easier by this would be x over x minus 1 over x. So when we get x minus 1 over x. So then when we flip it, this is x over x minus 1, which is x times x minus 1 to the negative 1. We probably could do that. I'm going to do that. This is going to be exciting. Are you excited? I'm excited. So we have dy dx. So basically what happened here was I just rearranged this to separate x on one side and y on the other side. So this is the little arrow, the product rule, uv prime plus u prime v, u equals x, u prime equals 1, v equals x minus 1 to the negative 1th power, and therefore v prime is negative 1, x minus 1 to the negative 2nd, which is the same as negative 1 over x minus 1 squared. And so dy dx then will equal let's see here. U is x, v prime is negative 1 over x minus 1 squared plus 1 times x minus 1. And then to get the common denominator, we'll do something like this. And we get something along the lines of x minus 1 minus x all over x minus 1 squared. So I wrote this one first and this one second, and I distributed the 1. And then this will give us negative 1 over x minus 1 squared. So let's see here. We could then probably write something in terms of y. So we could find, because we know that y equals x over x minus 1. All right, quick. X over x minus 1. Maybe we can do this. So this is negative x over x minus 1 squared plus, I'm going to separate the numerator. So we have, So this right here, so we had negative x plus x over x minus 1 squared, minus 1 over x minus 1 squared. Okay. We can totally do this. We totally got this. So equals, can we do this? Maybe we can do this. X over x minus 1 times negative 1 over x minus 1. Then we'll do plus the same thing. I know. Seems silly. Because I'm just distributing that. Minus 1 over x minus 1. That'll still stay squared. Yep, we'll go to that. So now, if we look back over here, this is way tangential at this point. Y equals x over x minus 1, x over x minus 1. So this would equal y times negative 1 over x minus 1 plus y times 1 over x minus 1 minus 1 over x minus 1 squared. And we could probably simplify that further and get the answer in terms of y. So, totally possible. That was way harder. That is not, yeah, okay. So, long story short, we see this problem. We're like, all right, they're on the same side. We can use implicit differentiation. Or we could try to rearrange things, make them work, and we could probably actually get it. We could get it in terms of y. But when you see x and y in terms of the answer, you probably want to use implicit differentiation. So this is how we could do it through the traditional method. And we did get an answer, but the multiple choice is looking for an answer in terms of y, which means that we'd have to take our y that we found up here, plug things in, and sort of rearrange things to get the way they want. A lot of times you see in math, and then a lot of times in physics, you can get the answer, but it's not in the form that they want. So what you do is you take all the knowledge you have, you put it in a box, you shake up the box, and then you look in the box, it's like, oh, okay, this is what I want. It's basically the same idea of solving the Rubik's Cube by randomly turning things and looking at it. And be like, nope, not right. And doing it again, and so forth and so forth. Not very efficient, and it takes a while. Okay, so we're going to do this through implicit differentiation. So the way to look at this is we will rewrite this as y to the negative 1 plus x to the negative 1 equals 1. So that's just y to the negative 1. So to take the derivative of both sides, we will do... So we'll take the derivative of everything with respect to x. So the derivative of y in this case, we start by doing the power rule. So we'd have negative 1 y to the negative second. But then we also have to do the chain rule here and find the derivative with respect to y. So dy dx. Plus, so what we're doing here is we're taking, I guess so this would be considered the partial derivative with respect to x. So we're taking the derivative of everything with respect to x. So then we do the same thing for x. So we have negative 1, x to the negative second. That's the power rule. Then we would do the chain rule, same with y, dx, derivative of x with respect to x, which in this case is just going to be 1. And then we'll take the derivative of 1 with respect to x. And since 1 is a constant, it just goes away. So rewriting this in a prettier fashion, we will have, let's see here, negative dy dx times 1 over y squared equals, and I'm going to move this over to the other side. This goes to 1, which intuitively makes sense because you see same number over the same number. So like 4 over 4 is 1. Dx over dx seems reasonable that it'd be 1. That's not a mathematical proof. It's just a, oh, well, that sort of kind of makes sense. And then rewriting this, we have dy dx equals negative y squared over x squared. And that's even a possible answer right there. So we have dy dx equals negative y squared over x squared. Yes, and that's how you do this part using implicit differentiation. And we could then rewrite that. Basically, we solve for y and then plug that value into here, and it'd be only in terms of x. So there's lots of different ways to write this. This is why the idea of writing an equation or an expression in its simplest terms kind of gets a little subjective and ambiguous, because simplest has to do with, well, what's your end goal for it? What are you going to do with it? And so what might be simplest for one application or problem may not be the simplest for another. And that's where that kind of gets convoluted. So for this one, implicit differentiation, one of the keys to see that that's the way you want to go is you have x and y in the answer. And so implicit differentiation, the idea of taking derivatives of everything, is kind of the route you want to take for this problem.